point of emphasis, well, actually a couple of them, would be the sandwich theorem, also known as the squeeze theorem. I don't know why I tried writing the script there. Squeeze theorem. And we'll get some review with that in a couple of minutes. But this is basically saying that if you have two functions that you know surround a third function, so a third function is sandwiched in between those two outer functions. If those two outer functions have the same limit, then they're trapping the third function in between them. That third function would take on the same limit. All right, so we'll see what that looks like in a couple of minutes. There's also some L'Hopital's rule stuff here, just a refresher on that. But it's very notation heavy, and so if you understood what I was saying before, then this is not, it would not fall under the category of required reading, I don't think. This one, these theorems below, this one is really important. This last one here, the one with the absolute value, is not as important, only because this really is the squeeze theorem again. It's just in a different form. So we'll see how we can get away with not really knowing this one. But these guys are very important because they're dealing with exponential functions. And when you're talking about exponential functions, it's the basis of what's known as a geometric relationship. So geometric series and sequences, their foundation is in exponential functions. All right, so you have arithmetic sequences and series, which has a foundation in linear functions. Geometric has a foundation in exponential functions. So if you know about exponential functions, you have a lot of context to understand geometric sequences and series. All right, so what this is telling you, these are little shortcut rules telling us that if you're finding the limit of some exponential function r to the nth power, so r is some numerical base. If it's a fractional base, then the limit's going to approach 0. So fractional as in the absolute value of it is less than 1. If it's a whole number base or some fractional value that's greater than 1, then it's going to approach infinity, so it's going to be a divergent situation. All right, and so I'll just give you a quick sketch of what they look like. And honestly, I'm not even going to sketch these sequences. I'm going to sketch the actual functions. So if I were to take something like y equals 1/2 to the x power. All right, what that's telling us is that for each consecutive x value, you're multiplying by 1/2. So if I start off with the first x value, so x equals 1, y would be equal to 1/2. X equals 2, y would be equal to 1/4. X equals 3, y would be equal to 1/8, and so on. In the form of a graph, now you could go all the way to the y-axis, but since we're going to marry this concept to sequences and series, we know that we're looking at positive integers. If I were to create just this function, I could do it continuous or I could do it by points. What I'm looking at are y values that are getting closer and closer to 0. So if I plot this as, let's say that this is 1/2, and we do 1, 2, 3, 4, 5, we'd be looking at 1/2, 1/4, 1/8, consistently half of its previous value. And I suppose you wouldn't necessarily want to connect the dots because if we're, like I said, going to marry this concept to the idea of sequences, we wouldn't want to account for the values in between. All right. So that's an example of something that would actually converge on a particular number, because eventually, if you could actually identify the location of infinity, but I said before, infinity is a moving target, so you're not going to, but the idea would be like, what are you aiming for in terms of a y value? You're aiming for 0. So the limit would be, if I were to write this as a limit expression, limit as x approaches infinity of 1/2 to the x power would be equal to 0. All right. And so that's the idea of having an absolute value less than a value of 1. Right? So then the other another possibility, I'll go with a simple case, y equal to 2 to the x. So x equals 1, y equals 2, x equals 2, y equals 4, x equals 3, y equals 8. So it's just a reciprocal of everything that we came up with in the last list. So if I plot 1 against its y value, it would be 1, 2. 2 would give me a 4. 3 would give me an 8. But then it wouldn't take too long before we're off the chart here. So we'd have 16. Now I'm not even going to plot it, but it would be somewhere in this neighborhood. 32 somewhere in this neighborhood. Then 64, then 128, then 256, 512, 10, 24, 2048, 4096, etc. Obviously getting larger and larger. So if x were to approach infinity, this would approach infinity also, the y value. All right? So that's an example. It's not a proof, but it's an example of a case where the r value would be greater than 1. So then you get into something like limit as n approaches infinity of r to the nth does not exist if r is less than or equal to -1. That's an interesting case. All right, so let me come up with an example of that. So let's say we have y equals, I'll go with -2 to the x power. All right. Now, you could definitely see issues that might emerge if you have fractional values of x, but we don't have to worry about that because we're only working with positive integers for x or n, depending on how you're looking at it. But we could also look at this as the product of two functions. Let me just bring that in a little. Y equals -1 to the x. And and then +2 to the x. All right. This component here leads to what we call an alternating function. All right. So depending on what the x value is, mosquito. Depending on what the x value is, the sign could be positive or negative. All right? If x is equal to 1, we have a negative sign. If x is equal to 2, it's a positive sign. 3 is a negative sign, and so on. So it's alternating back and forth between being positive and negative. All right? So, and it's getting absurdly large very quickly. So it's got the characteristics of this where the y values are getting absurdly large very quickly, but they're also alternating in sign. All right. So if I were to create a graph out of this, we would have, again, 1, 2, 3. I'll do 4 of them because 5, even that, it's still not practical. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, and then I just need to go 1, 2, 3, 4, 5, 6, 7, 8. So if I'm plotting points here, I'd be looking at, you plug in a 1, you're going to get a 2, but a -2. So that's going to put me right here. If I plug in a 2, I'm going to get a 4, but it'll be positive. 3 is going to be negative 8. 4 is going to be positive 16. All right. If I plotted 5, that would put me down here somewhere at negative 32. All right. So what's happening is the points are kind of fanning out. They're getting further and further away from the x-axis, but not in a particular fashion. All right. So yeah, they're doubling in their distance, but if infinity were a location and on top of that it was someplace I could get to, then how do I know that I would be at the positive infinity or the negative infinity that this is going to give me? So there's a disagreement. So I don't know if it's positive or negative infinity, so in this case the limit simply does not exist. All right. And that's the whole philosophical thing behind, like if you get infinity for a limit, isn't that the same as saying that there is no limit? Like there's no maximum, it never ends. So isn't that the same as saying that there is no the limit does not exist? That's not the case. Well, what we're talking about when we say a limit does not exist is we're talking about a contradiction. All right. So a fundamental disagreement. Infinity is a limit. All right. It's just a moving limit. You can aim for infinity. You can't aim for DNE. All right. Limit does not exist means that you could not possibly compute or determine what the limit is. All right. So these are the separate cases that deal with the geometric relationship, or in this case, because we're not really there yet, exponential functions. All right. So I mean, I can look at this because I have a lot of experience with exponential functions from teaching it or being a student, but more so teaching it. So it's pretty obvious to me, but like it's not always the kind of thing that comes naturally to people. So I encourage you to explore different types of exponential functions on your own. Take your calculator, type in 1/3 to the x, 2/3 to the x, 4/3 to the x, and see what's going on. Get a good sense of what's going on with the graphs. And that's going to help you when it comes time to explore geometric sequences. All right. So on the next page, what we need to do is determine whether the sequences converge or diverge. All right. If they converge, then give its limit. So basically what we're trying to do is determine the limit as n approaches infinity for each one of these. Right? Because if we're dealing with a set of positive integers, yeah, I suppose it could converge onto a particular value after like n equals 10. But if it's a function, if it's related to some known function, then it's probably going to ease its way into its limit. All right? It's not like a piecewise function where part of it could just be y equals 10. So that's your limit. That might happen very early on. You don't even have to get out to infinity in order to see that. These are different. These are more complicated. Some of them are not bad, though. Like, number 1, that's straight up L'Hopital's rule. All right? Because if I were to find the limit as n approaches infinity of n plus 4 over 3n minus 2, just by plugging and chugging away, I'd get infinity over infinity. All right, infinity over infinity or 0 over 0 is never a final answer. All right, it's an avenue. It's an approach. It's telling you that you can get a limit, you just have to do the work. All right, here it's telling us that L'Hopital's rule applies. So once you make that determination, well, apply the rule by taking the derivative top and bottom separately from one another. So with respect to n, derivative of n plus 4 would be 1. Derivative of 3n minus 2 would be 3. Limit of a constant is equal to a constant. All right, so it converges. All right, it converges, and it also asks us to give the limit if it did converge, so it I think I might have missed. Because I don't have guts all over my hand. It looked like it had kind of like a hard shell. And I also didn't feel like that satisfying crunch. Yeah. Alright, well anyway. Number 2. Limit. As n approaches infinity of n squared over e to the 4n. Well, if I plug in infinities, again, plugging and chugging away, I'm going to get infinity squared, which is infinity, and e to the infinitieth power, which is infinity. So L'Hopital's rule applies again. So derivative top and bottom, I'm looking at 2n over 4e to the 4n. All right, derivative exponential function, keep it as is and then multiply by the derivative of the exponent, which would be 4. All right, again, derivatives of the top and bottom separately, not quotient rule. All right, so good news, bad news. Bad news is if I plug in infinity at this point, I still get infinity over infinity. The good news is I can do something with that. It means L'Hopital's rule applies. Again. So derivative top and bottom. 2 over 16 e to the 4n. Until you get something that is finite. All right. So in this case, if I apply the limit, I'm going to get 2 on top, so that's not infinity. So one way or another, I'm at the end of this journey. On the bottom, if I plug in infinity, I'm getting e to the infinitieth times 16, which is infinity. So then the only thing I would need to know is what 2 divided by infinity is. Or what 2 divided by infinity approaches, because again, infinity is not a place. So you can't actually divide by it because it's not a number. But if I continuously increase the denominator of a fraction, what happens to the overall value of the fraction? What is it going to? 0. So it converges. Yeah, because if I start off with, like, let's say 2 over 10, that's equivalent to 1/5. 2 over 100, 1/50. All right, 2 over 1,000, 1/500. The fraction's getting smaller and smaller and smaller. All right, eventually till it gets to 0, if it could. All right, so L'Hopital's rule twice. So the next one must be L'Hopital's rule 3 times. For the denominator chain rule, yep. All right, so, yeah, I was just kidding. Number 3 is not L'Hopital's rule 3 times, because what you're dealing with here is the idea that you can't settle in on a particular number for the limit of the top as n approaches infinity. If I put cosine of infinity, it's like, okay, well, I don't know what it is. I know it's somewhere between -1 and 1, but I don't know where it is. So it would be one of those indeterminate situations, but not the word indeterminate, more like can't be determined. All right, so another approach is required. In this case, we use what's known as the sandwich theorem, or to make it sound less stupid, we call it the squeeze theorem, which only barely sounds less stupid. All right, so what I need to do here is figure out what 2 functions this one would be sandwiched or squeezed in between. And you're like, well, if I could do that, this would be a whole lot. Well, what you do, trig functions are a lot easier to handle when it comes to the squeeze theorem, because sine and cosine functions always exist, regardless of what is contained within the function. They always exist between two values. Two very specific values. The cosine and sine functions, I mean, if you were to graph a sine function, you put whatever you want inside of it. All right, cosine of pi x minus 3/8. It doesn't matter what you put inside. Pi x squared minus 3/8. It's always going to bounce back and forth between -1 and 1. All right. And that has to do with the amplitude of the function. Right? If this were 2 times the cosine of 5n squared, then it would bounce between -2 and 2. But a sine function, cosine function always bounce between -1 and 1. And then you might say, well, what about a tangent function, secant function, blah, blah, blah. And I would say, well, no, because those are infinite. Right? They go the other way. The only 2 functions out of the 6 trig functions that are finite in their range are the sine and cosine functions. Everything else is infinite in some capacity. All right. So I have this relationship. I can rely on this. But what I need is the limit as this approaches infinity. So what I'm going to do is I'm going to build this fraction from this inequality. You can multiply, divide, take a radical, whatever you want to do to an inequality, as long as you do it to each part of that inequality. All right? So what I want to do is divide each part by the square root of n. Okay, so now what I want to do is find the limit of each part of this inequality as n approaches infinity, which is more writing than you want to do, but it's got to be done. Limit as n approaches infinity of -1 over root n is less than or equal to the limit as n approaches infinity of that cosine 5n squared over root n is less than or equal to the limit as n approaches infinity of 1 over root n. All right, now I haven't been using my calculator just because I'm showing you these skills, which are important, but you know, if you're in a jam, go to the calculator. All right, but this is along the same lines as the previous one, where if I were to substitute in the infinity for n, I'd be looking at -1 over the square root of infinity and +1 over the square root of infinity. In each case, I get a result of what? 0. All right, so the outer functions have a limit that's equal to 0, both of them. We know that the inner function is squeezed in between those 2 outer functions. So whatever the limit is of the 2 outer functions, the inner function has to take on that same limit. All right, it can't escape from those boundaries. All right, so it's been squeezed within. So they came to 0 at infinity. So from the both ends, they came to 0, and then you have that inner function that's living in between. So it's literally being squeezed in between those 2 functions. And so once they get to a point where they're indistinguishable from one another, that third function must take on all the characteristics of the 2 outer functions, all right, including its limit. So my final answer here would be that the limit as n approaches infinity of the cosine of 5n squared over the root of n is going to be equal to 0, and that suggests that this is converging. And honestly, this is like the best example for converging, because it's converging in that the limit exists, but it's also like fitting what a person would think of when they think of the word converging. Right, two things coming together.
Will it always be from -1 to 1, or would it vary?
For cosines and sines, always -1 to 1. So actually, if you're looking at number 6, which I won't do now, I'll star that one, but that's also a squeeze theorem problem. You would start this one off by saying that the sine of 3 over n squared is between -1 to 1, and then multiply everything by n squared, and then apply the limit. I'll put a star on that bad boy. All right, numbers. You know what? I'll put a star on 4, 5, and 6. 5 is very scary looking, but it's not hard at all. Oh, you know what? If I'm going to do that, I'm just going to put stars on everything else. Because numbers 8 and 9 refer to the rules that we talked about on the previous page, r to the nth. If the absolute value of r is less than 1, then it converges. If it's greater than 1, it diverges. So like you can use that information to help you with 8 and 9. And this is a constant, so that's like nice.